The Nion is the new 1.2 megapixel time-of-flight camera from IDS, providing superior spatial resolution with reliable depth precision in even the most challenging of environments. If you are new to the product, there are some introductory videos available on the Vision channel already for you to view. This video is to provide guidance on setting up the Nion for use in IDS Peak Cockpit. The assumption at the start of this session is that the camera is already powered and connected to a PC and that the network configuration is taken care of. However, if you do not have the software downloaded already, you can download this from the IDS website, and the link is in the notes for this video. And if you need guidance on the Ethernet setup, there are details in the IDS Peak user manual, and again, the link is in the notes. Otherwise, all being well, when we start IDS Peak Cockpit, the camera icon in the top left corner should be active and we can open the Nion. Otherwise, all being well, when we start IDS Peak Cockpit, the camera icon in the top left corner should be active and we can open the Nion. We should see some data already, but we don't need to worry about what is displayed at this stage. We will come to the configuration soon. For now, check the camera is running by moving something in the field of view or checking the frame count is increasing, and that is enough. The first task is to set up the Peak Cockpit workspace, basically how Peak Cockpit appears and which configuration dialogues we need. There are a number of default dialogues, but we need to add one more dialog with some controls specific to Nyon. Start by clicking on the Generic Parameters button. And from here, we can create a custom dialog box that contains the parameters that we need to optimize the data. From the search bar, type Scan 3D to filter to the relevant parameters. Click on the Select Parameters button, and we see checkboxes appear next to each parameter. Scroll down to the last three parameters: Scan 3D Noise Filter, Scan 3D Range Confidence Threshold, and Scan 3D Range Flying Pixel Threshold. These Scan 3D parameters are used to optimize our 3D data, and we will explore what these actually do later. Click on the Apply Parameter selection, and a new dialog will appear on the left. We can then close the Generic Parameters dialog. We need to add a few more configuration dialogs that we will use for setup. So add Brightness and Frame Rate, Host Features, Save Load Parameters, Calibration, and Settings 3D. Currently, we have three data displays available. Image 2D is the intensity map, essentially a monochrome image which may be quite dark at first use. Image 3D, which is our height or range map. This is a 2D image where color represents Z, or the distance from the sensor. Here we can see also, as we move the mouse over the image, X, Y, Z values are displayed. We also have the 3D view, which is a point cloud generated in Peak. We can add a fourth display, which is the confidence map. Go to the Host Features dialog. The image component is used to select which components we receive from the Nyon. In the image component drop-down list, select Confidence Map. We have to stop the acquisition before the toggle switch next to the image component becomes live. Then we can enable the confidence map. This component shows the confidence in the accuracy of each point. Set the display color map to something colorful, like the jet profile. With this color profile, the closer to red the point in the image is, the higher the confidence, and the closer to blue, the lower the confidence. We can use this later for the optimization. Currently, we can switch between each component display, but we can also use a tile view by clicking on Enable Tile View. This displays all components together. This is a useful way to visualize the data and see the effect of changing parameters on each component simultaneously. If there is a preference for a full image view, drag the title bar for each window to the top left window, and this will restore the view to a single component view with the tabs to switch between each display. Now we can save the Peak workspace so that we can restore this view each time we start Peak Cockpit. Click on Create Workspace. give it a suitable name, and disable all of the toggle switches, and click Save. If we want Peak Cockpit to start automatically with this workspace profile each time, we can enable this in the Peak Cockpit application options under the Workspace tab, and then select the workspace from the drop-down list. We start the configuration with the intensity map or image 2D. The aim here is to optimize the image brightness without saturating the pixels. This is to optimize the 3D data, as the amount of light the sensor receives determines the quality of the 3D data generated. We can also optimize the display for viewing purposes. Switch to the Image 2D display and open the Brightness and Frame Rate tab. As we have all three components coming from the camera at the moment, we can reduce the frame rate down to around 15 frames per second to avoid bandwidth problems. We can adjust it back up to 30 frames per second after completing the setup and disabling the components we won't be using in the general use of the Nion. Set the exposure as high as we can without reaching saturation in the image to maximize the signal to noise ratio. If there are reflective objects in the scene, this may limit the exposure time. Also, if we are imaging moving targets, we may choose to keep the exposure time shorter to avoid motion blur. We can either adjust this by eye, or we can reference the histogram and use this to guide the image brightness optimization. If we are imaging a dark target that does not reflect back much light, we may also need to add analog gain to increase the brightness. Ultimately, the quality of the 3D data is dependent on a sufficient level of illumination reflecting back to the camera. And we can also reference the Image 3D component and confidence map to see how the exposure and gain affect the 3D quality, remembering that the higher confidence points will show colors closer to the right of the selected color map, and lower confidence will show colors to the left of the color map. For viewing purposes, if the scene is still quite dark, we can add digital gain. This is applied in software, so does not affect the 3D quality. So we can tolerate some saturation here for the sake of good visualization. If we switch to the host features, we can also enable gamma. Here, increase the values to around 2 or more, and this stretches the dynamic range in the image and will provide more contrast in the dark areas of the image. Again, this is in software, so it doesn't affect the 3D data. It's just for visualization. Now we can turn to the 3D components, the Image 3D and the 3D view. With time of flight, we have to talk about ambiguous data. Here, we are referring to data points where the distance cannot be reliably reported outside of a given range. This is managed by setting unambiguous ranges on the camera. For example, if the unambiguous range is set to 750 millimeters, features or objects within 750 millimeters of the camera will be reported correctly. If we have features or objects in the scene that are more than 750 millimeters away, these points will be reported as being closer to the camera than they actually are. This is because the phase shift between the transmitted and received signals are the same at that distance. By setting the correct unambiguous range, objects and features will be reported at the correct distance. It isn't always visually obvious in the Image 3D data, but in the 3D view, it appears as flying data closer to the camera. So before we start, we need to have some idea of the range we will be working with. We can either measure this, or if we switch to the Image 3D and move the mouse over the image, we can see the distances in the Z component. If we see an unexpected distance, this points to some ambiguities. In this case, we can see the boxes in the field of view measure between around 550 and 650 millimeters from the camera, but the surface the boxes are sitting on measure at around 20 to 30 millimeters from the camera, which tells us that our unambiguous range needs to be longer than the current setting. Switching to the 3D view, we can see these ambiguities appearing as data close to the camera. If there's no interesting data at the same distance as these ambiguous points, so closer than 600 millimeters where the boxes are, we could filter out the data in this range using the threshold Z minimum range under Settings 3D. Increasing this to around 250mm removes all of the ambiguous points, and we can still benefit from the higher spatial resolution and faster acquisition time of the shorter unambiguous range. As we increase the unambiguous range, the trade-off is either the Z accuracy is reduced or the camera switches to a lower resolution mode and uses a dual frequency, increasing the acquisition time. We will learn more about the different modes and how this affects resolution, accuracy and precision in a separate session. We will see more about the filtering later in this session, so for now we should reset this filter and instead load a different unambiguous range that fits our application. Go to the Save Load Parameters dialog, and in this case we can load the 1.5 meter range UAR 1500 quad VGA. The other unambiguous ranges available will also be covered in another session. One thing to note is that when we load a new unambiguous range, the settings we set for the intensity view are reset, so we need to set these again. We need to go back and set the frame rate, exposure and gains, or these can be loaded from file, and we'll see this next. The range should now be correct. We can check this in the image 3D by moving the mouse over the image and checking the Z values are as expected. And in the 3D view, there should now be no incorrect 3D data points flying around. At this point, it is a good idea to save these parameters. From the Save Load Parameters dialog, click on Save next to the Save Load Camera Parameters to File section. Give the parameter file a meaningful name that we can recall later, and click Save. This gives us a quick way to get back to known settings. We can also save the settings to the Camera User Sets area and set the User Set 0 or User Set 1 as the default startup parameter set, but note that as the digital gain and gamma are software settings from the Peak IPL, these are not saved to the camera and need to be set each time in Peak Cockpit or through the Peak IPL. Now, a few points about the 3D view. To change the view, we can click and hold the left mouse button and then move the mouse left and right or up and down to navigate around the point cloud. Here we can also click and hold the right mouse button and move the mouse to shift the point cloud up and down, left or right. At the moment, the origin of the data, the zero distance, is at the camera. This is indicated by the red, green, blue cross. When we rotate or pan around the point cloud, there is another red, green, blue cross, this time within a sphere. This, by default, is at the point cloud origin, but by shifting the point cloud, we can adjust this sphere to center around a plane or specific object in the point cloud, making it a bit easier to manipulate. With the wheel on the mouse, we can zoom in and out of the point cloud, and if we get a bit lost in the point cloud view, we can reset the views in the Settings 3D dialog. There is a Reset View option and several standard views. Above this, we can also set the point size of the point cloud. I like to make these points as small as possible because it just looks a bit cleaner to me, but it's just personal preference. We can also disable the coordinate origin cross if we wish. With the 3D view currently showing in the Settings 3D dialog, we can change the color representation. The colors in the image are for visualization purposes and can be set to match the colors used in the image 3D or range map. And more importantly, with the min and max settings underneath, we can change how these colors map to the distance range. At the moment, the colors blue to red are mapped to the entire distance range, with blue closest to the Nyon and red furthest. In our scene here, we are only interested in the range of about 400 to 800 millimeters. So to get more color contrast in the scene, we can set the min to around 300 and the max to 1000 to allow for a little variation in the scene. So now blue will be at around 300 millimeters from the camera and red at 800 millimeters. Now we have more colors in the 3D representation, giving more contrast. These values also affect the image 3D view. The previous adjustments were affecting the colored data representation in Peak Cockpit. We can also filter out data in the point cloud to either remove ambiguous data if we want to benefit from the shorter unambiguous ranges, or simply to reduce the amount of data any algorithms will have to subsequently process. Still in the settings 3D dialog, we have the Z thresholds. These are the same as the color map min and max values, but will clip the data in the point cloud or 3D view. As before, we can limit the Z range to just the range we are interested in. Here we could cut out the background in the field of view, and in the 3D view this removes the data. In the image 3D view, we can choose to highlight cropped data in a color of our choosing, or we can continue to show the data, even though it is cropped in the point cloud data. If we want to reduce the amount of data transmitted from the camera, it is also possible to set a region of interest on the sensor from the position and size dialog. Back again with the 3D view. If we rotate the point cloud, we can see some data between the top of the boxes and surface the boxes are lying on. It's not truly representing the side of the box. These are known as flying pixels and occur on surfaces that are close to perpendicular to the camera, and it's not clear if a point belongs to one plane or another. From the custom parameters dialog, we can reduce the scan 3D range flying pixel threshold to a level that then removes these points. Reduce this right down and these points disappear. In the image 3D display, we can see a clearer edge. It depends on the application if we should use this filter or not. The noise filter can be used to smooth out smaller gaps or inconsistencies in the range map for more challenging surfaces. In the image here, there is a black box which is producing noisier results compared to the white boxes that are reflecting more of the light back to the camera. We can therefore increase the noise filter to smooth out and connect this surface, providing a more complete point cloud. Like any smoothing filter, this is at the expense of high frequency data, so there will be some reduction in spatial resolution. The last parameter is the scan 3D range confidence threshold. We can use the tile view again, so we can see the confidence map and the image 3D at the same time. To recap, the confidence map shows us how confident we can be in a point. Depending on the color map, this shows the confidence mapped against color. In this case, the closer to red, the higher the confidence, and the closer to blue, the lower the confidence. We can use this confidence threshold to remove data that does not meet a desired level of confidence. Typically, this will be due to reduced reflectance of areas in the image due to distance or the reflectivity of the target. When imaging a flat plane, we can see the edges of the image have lower confidence due to increased distance and angle of reflectance. In the corners here, we can see areas of blue which indicate lower confidence, and as we increase the confidence threshold, these points are removed from the image 3D and 3D view. As the threshold increases further, more points are removed. If we increase the exposure to increase the confidence, when the image starts to saturate, the confidence drops on these points, and so they are filtered out. And one feature of time of flight is called multipath interference, where the light can bounce off multiple points before returning to the sensor, producing inaccurate measurements. The confidence threshold can be used to filter out these points too. With our current setup, the camera is perpendicular to the target surface, and all coordinates are in reference to the camera, i.e. the closest point is directly at the camera. If the camera is at an angle to the reference plane, or we just want to transform the data to a different reference plane, for example, the surface where the boxes are lying, we can run a workspace calibration. For this, we need a calibration plate and to place this in the camera's field of view. Then open the calibration dialog and click on Run Wizard. The first page outlines the requirements and steps, and the second page provides only one option, so we can click through to step 2. And if the calibration plate is not visible due to a shorter exposure time, we can enable the manual brightness settings and either manually increase the exposure time or enable auto features until the target is detected and a green box appears. Click onto step 3 and click Apply to apply the workspace calibration. And we can also save the calibration parameters at this point. We can also do it later. In the image 3D display, the calibration target is now our 0 reference. Everything beyond the 0 plane will have a positive value, and everything closer to the camera will have a negative value. and there will be a flat color across the 0 reference plane, even if the camera is an angle to it. And we can save the workspace calibration to a file to be restored later to multiple different cameras, and we can reset to factory calibration where the camera is returned as the 0 reference. Image saving is possible by clicking on the Save Image button in the main display window, providing a file name and setting the desired format. The 3D view is saved as a PRY file. The other components are saved as simple 2D images. So we've covered the initial steps for setup here. Once the setup is complete, all parameters can be saved to the camera or to file for loading at later stages, or we can store different configurations for different scenarios. The second video in this series will go into more detail regarding the operating modes or the unambiguous ranges and how these modes affect the 3D data to help with choosing the right mode for your application. Thanks for watching.